we're doing today is almost like review, stuff that we hopefully understood from yesterday's class. All right, folks, hopefully we're ready to go. All right, a lot of words here. And again, I should point out, I forgot to post a link to the Math Video Library, that there is a Math Video Library website that I've been using for a couple of years, not just because of the pandemic, but I've been using it for a while. And there's a lot of useful material on there, including the handouts from the classes. So like today's class's handout is on that Math Video Library. If you just Google Math Video Library, you'll find it, but I will post a link to your D2L for it. Anyway, let's get going. So yesterday we talked about odd degree functions. So and we know what a degree of a function is. Any function that has an odd degree, and I'll use an example of maybe a linear function. So y equals 3x minus 1 is a linear function, and that has an odd degree because the exponent, the highest exponent, is x to the power of 1. So anything I'm talking about here, I'll give you another example. Y equals 2x cubed minus x. That's another odd degree function. So everything I'm about to talk about here will apply to both of these two functions. So if the coefficient, the leading coefficient, so this number right here, is positive, which it is in both cases, then this graph is going to go from quadrant 3 to quadrant 1. Right? That's exactly what we talked about yesterday. And we know, of course, that the quadrants refer to, this is 1, 2, 3, 4. So it's going to go from this quadrant here to this quadrant here. Doesn't mean it doesn't pass through other quadrants, but it means that its end behavior is that it goes from quadrant 3 to quadrant 1. So we talked about all of that yesterday. These two functions, both odd degree functions, both with a positive lead coefficient, they both go from 3 to 1. That's their end behavior. If it's negative, though, then it means that it goes from 2 to 4. So it goes from, instead of from 3 to 1, it goes from here to here, right? And remember, we always read from left to right. Always go from left to right. Now, let's talk about some other things that we didn't really get into yesterday. X-intercepts. For an odd degree function, it has anywhere from 1 to a maximum of n x-intercepts, where n is the degree of the function. So what that means is that a degree 1 function can have anywhere from 1 up to, well, only 1, because the degree of the function is a 1, x to the power of 1. So it cannot have any more than 1 x-intercept if it's a degree 1. If it's a degree 3, then it can have either 1, 2, or 3, meaning that the maximum number of x-intercepts it can have depends on the degree of the function. The degree of this meaning it's 3 or is 3, which means that it can have up to 3. So I'll give you an example of what that might look like. Here is a degree 3 a cubic function that looks something maybe like this. And as you can see, it has 3 distinct x-intercepts, one here, here, and here, but it might have 2. What if it looks like this? Right? Where it bounces here, then it goes through here. So it touches at one spot, then goes through. So that's only 2 x-intercepts, or it could have 1 x-intercept. So maybe it looks like this. Oh, sorry, that's not right. Let me erase that. It might look something like, I'll use a different color to draw it. It might look something like this, where it only touches in one spot. And that goes for odd and even degree functions. No, we're going to get to the even degree functions in a while, Noah. Can you please give the definition of an odd degree function again? Kayla is asking. Odd degree functions are functions where the highest exponent is an odd number, right? So I gave you 2 examples, 2x cubed minus x. Even though there's another exponent on this x, which is assumed to be at x to the power of 1, the fact is that the highest power here, what I'm pointing to, is 3. So that makes it an odd degree function, because 3 is an odd number. Okay, Kayla, does that help you out? And thanks for the question as well. Okay, great. So I gave you 3 different possibilities. It either goes through at 1 x-intercept, or 2, or 3, but it can't get any higher than 3 if the degree is 3. But how about 0? Is it possible for it to have no x-intercepts? Is that possible? You know, like we have some quadratic functions that have no x-intercepts because they just turn around and go back. Is it possible for an odd degree function? Noah says no. Why would you say no, Noah? What makes you think it must have an x-intercept? Why can't it have none? We've seen quadratic functions that have no x-intercepts. I know those are even degree, but Why are you saying that it must have at least one for odd? Can you give me a reason why that is? Because they always go up or down, even though it's going in one direction. Okay, and you're absolutely right. I'll read what you said because what you put in the chat is not going to be on the recording. It says what Noah is saying is that because they always go up and down, but even degrees go in one direction. So what you're saying is that if they're going to go up and down, then the only way that's going to happen is if they cross through the x-axis at some point. It has to pass through the x-axis if that's the case. Going from 2 to 4 or going from 1 to 3. And by the way, you don't go from 1 to 3. And you just so we're clear, because you can't go, you're reading, yeah, you have to go 3 to 1. I just want to make sure you're clear. I don't want you putting 1 to 3 on a quiz or a test. It's 3 to 1 because you're going from left to right. Just remember that, please, Travis. Okay, sorry, Janaya, please go ahead. Okay, so what we're saying is that these odd degree functions either go from 2 to 4 or 3 to 1, right? So in going from 2 to 4, let's do a quick little thing here. 2 is over here and 4 is down here. There is no way for you to go from 2 to 4 without crossing the x-axis. You see what we're saying, Janaya? There's just no way. There's just no point. You can't start in quadrant 2 and end up in quadrant 4 without crossing the x-axis. Does that make sense? And the same thing if you're going from 3 to 1. If you're going from 3 to 1, you can only do that by crossing through the x-axis. So all odd degree functions all have a minimum of one x-intercept. And the maximum is whatever the degree is. So if it's a degree 3, then it's going to have up to 3. Does it have to have 3? No. I said to you a while ago, I gave you 3 possibilities. Here's a cubic function, which only has 1. Here's a cubic function that has 2. Here's a cubic function that has all 3. So you can have anywhere from 1 up to whatever the degree is. So degree 3 can have either 1, 2, or 3. Okay, so let me keep, sorry, go ahead. Well, a degree can be 0. Let me stop you for a second. That's not true. A degree can be 0. Here is a degree 0 function. Y equals 6. That's a degree 0 function, right? Y equals 6. There's no, you can say that there is maybe a hidden x to the power of 0 there if you like, because x to the power of 0 is 1, so that's just 6 times 1. But y equals 6 on its own is a degree 0 function, just so we know. I'm glad you brought that up, Jeremiah, please go ahead. That's a good question. And most people consider it to be even because they think of 0 as being like an even number, an even degree function. So there's a bit of sort of this debate on that one as to whether we should include that in even degree functions. So it depends on what side of the debate you choose to go on. Functions like quadratic functions and quartic functions, there's no debate there. Those are even degree functions. Do we include 0 degree? There is some debate there. Let's put it that way. Okay. All right, so let's go back. Let's go back to this. All right, so we talked about x-intercepts. So from either 1 to a maximum of n, where n is the degree of the function. Domain and range, let's just talk about that. Let me erase all of this here. Turns out that the domain and range for all odd degree functions is unrestricted, completely unrestricted. Okay, let me see. What would you include for 6? Or would you just put not? Yeah, you could put 6 because, like I was saying, it's like saying 6 times x to the power of 0. So you could say that the x to the power of 0 is assumed, and the 6 is the coefficient. Okay, all right. Okay, so where am I? Domain and range. So unrestricted, XER, YER. Right? That's what the domain and range of an odd degree function is. Now, having said that, if the odd degree function is modeling something which, let's say, relates to maybe time or some other distance or something like that, there may be a restriction that is imposed by the model. So you might say that time cannot be negative, for instance. But if it's just a typical regular sort of odd degree function, then we consider it to be unrestricted. There is no limit on the range. There is no limit on the domain. There is never an absolute max or min point. So because it goes up indefinitely and down indefinitely, right? It doesn't have a max, it doesn't have a min. You talk about maxes and mins when you were doing your quadratic functions back in grade 10. But this one has no max or min. A function that looks like this, right, goes down forever and goes up forever. There is no max or min. But it could have what we call these local maxes and local mins. So there's no, what is called, there are no absolute max or min, right? That's what I'm underlining there. There's no absolute max or min, but you can have local maxes and mins. So if you look at the things that I've just circled there, it looks like it's kind of a max that you would have on a quadratic function or a min on a quadratic function. But the fact is that it's just a max in that one little area right there. So that's why I call it a local max. This is just a min in this one little area right here. So we call this a local min. So no absolute max or min, but you can have local maxes or mins. And the number of those local maxes or mins is going to be limited by what we call n minus 1. N minus 1 means a degree minus 1. So for instance, if it's a cubic function, it can have up to 2, which is n minus 1. So 3 minus 1 is 2. It can have up to 2 of these local maxes and mins when you add them all together. This has one local max, and it has one local min. When you add those together, you get 2, which is what n minus 1 refers to. Would local max or min be almost known as relative max? Yeah, that's fine. You can use that as well. All right, so local, relative, I can accept that as a way of describing Jeremiah's question is. Okay, it may, I'm not saying it must, let me underline the word may. It may have point symmetry. We talked about point symmetry yesterday. So not all odd degree functions have point symmetry, but if it's going to have symmetry, it's going to be point symmetry rather than line symmetry. Okay, so let's move on. That's odd degree functions. Let's get to even degree functions now. If it's a positive leading coefficient on the even degree function, then yesterday we said it goes from quadrant 2 to 1. We talked about that already yesterday. The range is restricted. So if it's a positive lead coefficient, so I want you to think of like a quadratic function, which is an even degree function. Quadratic functions are even degree. And let's think of one that maybe looks like that. Going from 2 to 1, starts off in quadrant 2, ends up in quadrant 1. The range of this is going to be there's going to be some minimum value if it's a positive lead coefficient. As you know, if there's an a that's positive on a quadratic function, it does have a min value. So whatever this point here that it reaches to will represent the lowest minimum y value. So that's why they say that it's going to have a range where y is greater than everything that's above it, greater than whatever that minimum value is. Okay? So there's no restriction on the domain, but there's a restriction on the range. The range is going to be limited by saying that y has to be greater than some number, whatever that minimum value is. Now, so there's going to be at least one minimum point, but if you include all the mins and the maxes, right? So like how they have the local mins and maxes for the odd degree functions, if you include all of those, then you would have n minus 1 of those. So let me give an example. Let's say we had, I'll use a quartic function, right? Quartic is an even degree function. So let's say it looks something like this. So it does have an absolute minimum right here. But there's another little minimum point right here as well. And there's also, and I'm talking about a local minimum now, there's also a local maximum right here as well. When you add all of those together, which is 3 in this case, and that's your n minus 1 when you put all your mins and maxes together. So sometimes I call them turning points. When you get into calculus, most of you are probably doing calculus, you'll hear terms like turning points rather than using mins and maxes. And what we're saying is that it can have up to a maximum n minus 1 of those. Okay? All right, so that's for positive lead coefficient. For negative lead coefficient, it goes from quadrant 3 to quadrant 4. The range is going to be y has to be less than something. So whereas this one had a minimum point, the other one is going to have a maximum point on it. And again, it has at least one maximum, but if you include the mins and the maxes, it's still the same n minus 1 in terms of when you group together all the mins and the maxes. Some local, some absolute. terms of x-intercepts, it's kind of similar to the odd degree functions, but it can have 0 x-intercepts. So I want you to consider for a minute if you had, we'll use the case of a quadratic function. Quadratic function that looks like this. Remember, that's an even degree function. This has no x-intercepts. That has, and you've seen those functions before. They don't even touch the x-axis at all. They start up here and they end up there. So they don't, because they turn, they never really have to go through the x-axis. Some of them do. So you can have the case of it just touching the x-axis. You can have the case of it going through the x-axis. So you have all three possibilities, right? You can have no x-intercepts. You can have up to a maximum of whatever the degree of the function is. So if it's a degree 2, so this is a quadratic here, it can have up to 2 x-intercepts. So it could either be 2, 1, or 0. So can you see the distinction here between odd degree functions and even degree functions, where odd degree functions have to have at least 1 x-intercept, whereas even degree functions don't have to have x-intercepts at all, right? They can have 0. They can go up to whatever the degree is, but they can have none whatsoever. Hopefully that makes sense. Okay, now the domain of all even degree functions also XCR. So there's no restriction on the domain, but there's a restriction on the range. It's going to have some absolute max or some absolute min somewhere, right? For all even degree functions. It doesn't go on forever on the y-axis. It stops at some point and turns around and goes back in the opposite direction. If it's going to have symmetry, it will have line symmetry, right? So remember I said earlier on that if there's going to be symmetry for the odd degree function, it will be point symmetry. Now I'm saying that if there is any symmetry on the even degree functions, it will be line symmetry instead, but not point symmetry. Okay. Now let's get to so that's some of that we just talked about is actually a review from yesterday. So nothing new from in terms of end behavior, but we're now learning about their domain and their range. We're learning about the turning points, and we're learning about which ones have maxes and mins and so on and so forth. Okay, so that's some of that stuff is new. Now let's get to finite differences. What you're seeing here is not going to make a lot of sense until we actually start doing it. But I'm going to just read it through, and we're going to come back to it later on, and it will make more sense once we actually start doing it. But it says the nth finite differences are equal or a constant when they have the same sign as the leading coefficient and are equal to a times n minus 1, where a is the leading coefficient and n is a factorial. So this is the formula that you're going to be using in a little while. So the finite difference, and I'll explain what that means in a little while, is equal to the LC, leading coefficient, multiplied by n factorial. Now, what is factorial? Everybody grab your calculators, please. Everybody grab your calculator. So far, I know we haven't really talked about what these finite differences are, but you do kind of know what they are, right? Do you remember back in, I'm going to say grade 9, I haven't taught grade 9 in a while, but do you remember back in grade 9 when your teacher told you about finding the first difference or the second difference and the third difference? Jeremiah, your hand is up. Go ahead, please. Mm-hmm. No, 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 not at all. I'm going to give you numbers where the factorial is probably within 10, if that much. Okay? So I'm never going to ask if if you're worried about you having to work with a factorial for yourself with like 1,000, so 1,000 times 99 times. No, I'm not going to give that to you. Plus your calculator key will do it. Did you not find the factorial key on yours? It's got to be there somewhere. All scientific calculators have one. Did you find it on yours? No, no, we're not going to go up to 1,000 or even no, nothing as big as that. Okay, let's get back to this. Now, those of you doing data management will definitely come across factorial because it's one of the things that you use to work out permutations and combinations. I'm not sure if anybody's doing data management now or plan to do it. then this is not the first time you're going to see factorials. So let's talk about differences. So let's go back to grade 9 for a bit. And let me ask the class. Your teacher might have said, here's a table of values, and I want you to find the first differences for your y's. What were they asking you to do back then for those first differences? Anybody remember and then what does it mean when you get those first differences? What is it hopefully able to tell you? What are those first differences, get my tongue all tied up here, able to tell you? First of all, what are first differences? Does anybody remember what first differences are? And sometimes you have to go to second differences and third differences and so on. What are first differences? Subtract the values, and don't they mean that they have the same slope? Okay, so Noah is certainly on the right track. Subtract which values? Is the x values or the y values? Which ones are we subtracting here? Anybody remember? The y's? Yes, Kayla. Well done. So we're going to subtract the y's. Now, the order in which you subtract actually makes a difference. Now, what I mean by finite differences is the column that you get to when you're doing, first differences, second differences, and third differences, and so on. The one that you get to where the difference that you get is the same for all of them. Now, when you're doing first differences, what happens if the first differences are all the same? I see that Noah said something about that they have the same slope. If they have the same slope, what is that telling you then? If they have the same slope, it's linear. Thank you, Kristen. Well done. But what about if the first differences were different, but my second differences were all the same? Then what does that mean for second differences being all the same? Right? So first differences were not the same. So Kristen says it's quadratic. You're right. You're right. All right. So hopefully you're following what Kristen is saying. Kristen is saying if the first differences are all the same, it's linear. If the second differences are all the same, then it's quadratic. So what do you think would happen if it was the third differences that were all the same? So first differences were not the same. Second differences were not the same. And Noah, you're right. You're absolutely right. If the third differences are the ones that are the same, then it's cubic. The pattern continues to cubic, and so absolutely, Jeremiah, absolutely. So if there's a fourth differences, it's quartic, and so on and so forth. There's a lot of number crunching to get this number, but whatever that number is that you get, which repeats itself, is what we call the finite difference. Finite means you have come to a point when you can't go anymore, because if you keep subtracting after you get to that number, which is the same, you're just going to get zeros. Because if all the numbers are the same, then subtracting those numbers from each other is just going to give you zero. So the finite difference is the difference that you get to when all the numbers work out to be the same. So let me take you now to your first table that you're going to be working on with me, which is not this, which is not that, which is this. If you had downloaded the thing that I put on the Math Video Library, then you probably have this printed off in front of you. Or if not, you're just going to have to work with what's on the screen here. So what I have here is some first differences calculated. Now, watch the order, take your calculator out, and make sure you're ready for this. Okay, here comes my regular little check-in now. I like to check in with the room from time to time. Okay, so Axa, are you there? Just want to make sure that people are staying on top of things and are with me here. Great. And how about Ava? Is Ava there as well? Where are you, Ava? Are you there? Thank you. Okay, perfect. So here's how this works. Now look at the numbers. It's 151 and it went down to 61. So your differences should be negative. And how do you get the differences? You take each number, I'm going to circle the 61, and you subtract the one that is in front of it. So the 151. That's where that minus 90 came from. All right, let me say that again. You don't subtract down. You don't say 61 minus 15. Don't say 15 minus 1. You take the number in front of it. Your number, the sign of the number should reflect what's happening to the y's. These y's are dropping. So they went from 151 down to 61. So that should be a minus 90. Went from 61 to 15. That's a minus 46. You went from 15 to 1. So that means you're dropping again by 14. Now look what happens when you go from 1 to 7. That difference is now 6. Okay? That difference is now 6. So if you were to fill in that column, I'm going to ask you to do that for me right now. Everybody grab your calculator. I'm going to ask you to fill in that column. So I have the first few numbers in for you. We'll get to the second difference column in a minute. But everybody grab your calculator. I'm going to be asking one of you in a minute And yes, the wheel is going to make an appearance shortly to fill in, give me some numbers to fill into that chart. And all I'm asking you to do is to do some subtractions. That's all I'm asking you to do on your calculator. Regular, basic, grade 3 subtractions. Just make sure you do it in the right order, right? That's all I ask. Make sure you do it in the right order. So everybody do that for me right now, please. Going forward from there. And the lucky contestant in our little game show here is Brooklyn. Brooklyn, can I get the next number after 6, please? After the one I've just circled. Brooklyn, are you there with us? You can't see what? What do you mean you can't see it? Oh no, I don't, because if I went back and forth with the wheel, then it would stop the recording. So I can only record one window at a time, so I don't share the wheel. But I can assure you that the name that's on there is Brooklyn. So Brooklyn, are you there with us? Where is Brooklyn? Brooklyn, looking for Brooklyn. Earth to Brooklyn. Where are you, Brooklyn? You're supposed to be in class and attentive and all that good stuff. Where are you? Where is Brooklyn? All right, we're going to have to come back to Brooklyn, but I do make notes of when I'm calling on students and they're not there. One night when I call on anybody, they're supposed to be there, ready to respond. All right, so we'll keep Brooklyn in there for now, and we'll go to the next person. All I'm asking you to do is a subtraction. That's really all I'm asking you to do. And this person is Janaya. Janaya, you are usually on top of things, so let's get you to give me your Wi-Fi was really slow and laggy. Okay, Janaya, hold off for me, please. Brooklyn, can you please give me the next few numbers in that first difference column, please? So after 6, the one I've circled, what's the next number after that? So minus 14. Remember what I said though, if it's going up, which it is, to go from 7 to 21, that number should be positive. Does that make sense, Brooklyn? You should be taking the 21 and minusing the 7, right? So it's a number below minus a number above. So don't subtract downward, subtract upward. Make sense? So let's try that again. So what would your answer be this time? And let's all be patient, by the way. I've always stressed that. So 14, I'll put that number in. Next one, please. Keep going, Brooklyn. Next number. Okay, good. Okay, thank you very much. I'll take you out of the wheel for today, just for today. Janai, you are next up. So let's get your response to, I already put the 6 in. So let's get your response to the number after, not the 6, sorry, the minus 6. Can I get the next number after the minus 6, please? Good. And the next number after that? Negative 74. Clearly, this is not a linear function. That's just not the case. So let's go across and look at second. Thank you very much, by the way. Let's go across and look at the second differences. Now, it's the same principle. We're just going to subtraction. We're just doing a bunch of subtractions. So, for instance, this 44 came from taking minus 46 minus negative 90, which is the same thing as saying minus 46 plus 90. You're minusing a negative, it means you're adding it. The 32 came from the same source. Yes, Janai, please go ahead. Oh, does anybody have an answer for that question? The question she asked is, how do we know it's not linear? That's the question. How do we know it's not a linear function? All right, Jeremiah, please go ahead. Absolutely. Wow. Okay. Well done. Well done. Well done. Yeah, that was excellent. Okay. Thank you very much, Jeremiah. You can take your hand down now. Perfect. Okay. So hopefully that answers the question, first of all. And let's continue now to the second difference column. I showed how to get the first 3 numbers, the 44, the 32, and the 20. I'm going to make sure that I'm going to go to my wheel now and ask for the next few numbers after that 20. This is clearly not going to be a quadratic function either. This one goes to Travis. Travis, are you with us? Are you there, Travis? Where is Travis? Perfect. Can you give me the next number, please? In the second difference column. Yes. That's just 14. Yeah, 14 and 6, correct. Positive or negative? Good stuff. Give me the next one, please. Good. Thank you very much, Travis. Well done. And Travis comes out. Hopefully everybody's following along and, understanding what we're doing here. And I'm going to ask for the next person just to finish up for us, please. And that would go to, this looks like Jeremiah. Jeremiah, it's your turn. Can you give me the next few numbers, please? What's the next number? Keep going. Okay. Keep going. Okay, thank you very much. Okay, so we've already decided, if you listen to Jeremiah earlier on, you remember that this is not quadratic either. Whoa, so we got some more work to do. So let's go to the third difference column and see if we can figure out whether this might be cubic then. Because remember, whichever column has the finite difference. Finite means it's when you get to the end. That's what finite means. You've infinite means you go on forever. But finite means you stop at a certain point. So let's see if this is going to work. We're going to follow the same principle. So the first number I gave you is a minus 12, which is a 32 minus the 44. That's where the minus 12 comes from. Let me go over there now, take out Jeremiah, and let's see who my next, sometimes I say victim, but that's such a harsh word. I should probably stop using that word. And let's talk to Isaac. Isaac, are you there with us? Is Isaac there? Where is I? Perfect. Isaac, give me the next few numbers, please. What's the next number after that? They're all minus 12s. Interesting. Is everybody getting that? That they're all minus 12s? Try a few more and see. Okay, good. So what is the conclusion that we can draw from this? The conclusion that we can draw from that is that the FD is equal to minus 12. That's what finite difference is. And FD is a third difference, so this is cubic. This particular FD is in the third difference column. Well, let me go back. I know this wasn't making sense to you earlier on. Okay, I'm going to delete this. And I'm going to delete that. Now this is going to make a little more sense. It says that the FD, this minus 12 that we're getting, is equal to the LC, and LC stands for the lead coefficient, times n factorial. So n refers to the degree of the function. So it means that we can get the lead coefficient for this particular function. That's what it means. This FD is minus 12. Is equal to the LC. We don't know the LC yet. Multiplied by, so what factorial are we going to be using then? What's our n in this particular case? The n is 3, so it's 3 factorial. There you go. So we now have a way that we can actually calculate what our LC is. We don't know the actual function yet. Later we are going to work the function out. But right now we know that the relationship between the lead coefficient and the finite difference is through this factorial thing. So let's solve this. So minus 12 is equal to the LC. What is 3 factorial? All right, you can use your calculators, or you can even multiply it out for yourself. What is 3 factorial? Anybody? I'm not asking anybody in particular right now, just anybody. Perfect, thank you, 6. So guess what? My LC is equal to minus 12 divided by 6, or minus 2. So I now know what the lead coefficient of whatever function generated this table of values, right? Whatever function generated this table of values that I'm looking at, that's circled in red, I know two things about it. I know it's cubic, and I know the lead coefficient is minus 2. That's actually enough for us to get the actual equation. But more of that later on. We'll get to that later on. Here's my challenge for you. I'm going to be muting my mic. It's the degree of the function. Okay, yeah, right. So no answer the question. Yeah, okay, good. Okay, good. Okay, so my challenge for you now is to follow the same steps for this function and tell me what the LC is of this function. I want to leave this on the screen. Everybody, and I'm not telling anybody who I'm going to be calling on next, until everybody's had a chance to do this. Everybody needs to grab their calculator, figure out which column gives you the finite difference, use that finite difference to, can I go up? Can I go up? I'm at the top of the page here. I'm sorry, I can't go up from here already. I can go to the page before that, but not up because there's no up here already. Make sense? You want me to go to the page before? Is that what you're asking me to do? Okay. All right. So we figured out the finite difference. That was a minus 12. So it's cubic. So then we set it up into the formula, which is that the minus 12, the finite difference, is equal to the lead coefficient times n factorial right here. And n factorial is 6. 3 factorial is 6. Then we worked out the LC from there. It worked out to be minus 2. Okay? All right. Janaya, please go ahead. 3 factorial. Remember the key on your calculator, the 3 factorial? It's not a minus 1. It's 3 with a little exclamation. What do you call it? Exclamation? Yeah, exclamation sign. So look at your calculator key for that. Remember I showed it to you on my calculator? And Travis is also, right. And Travis is also pointing out the same as 3 times 2 times 1. So if you're ever stuck and, in a hurry and you can't find a factorial key, just take the number and multiply it by all the other numbers descending from there. So 5 factorial is 5 times 4 times 3 times 2 times 1. So 3 factorial is 3 times 2 times 1. Okay? So in this case, it would be 6. All right. So I'm going to turn things over to you now. Here's a table of values. I want you to, I've already established it's not linear because I've already worked out the first 3 numbers for you, and it's clearly not linear. It's also clearly not quadratic. Is it cubic? Is it quartic? Is it quintic? I know it's going to take a while for you to get there, but I need you to do this for me right now, please. Bit of number crunching. You can copy down the numbers from the table, or if you want to write on your screen, if you have one of those Chromebooks that you can write on, whatever you want to do. I'm going to mute my mic now, and if anybody has any questions, I'll try to answer them. But what I needed to do is to finish the first difference column, go to your second difference column. You obviously need to go to your third difference column. Do you need to go further? I don't know. You'll find out. Nobody put their answer in the chat, please. In fact, I want to turn the chat off for now. Right? I don't want anybody making the mistake of putting an answer in the chat. I'm going to give you a couple of minutes to do some number crunching, and then I'm going to come back to you. So my mic is now on silent, mute for a bit, while I give you a chance to get this done. But I can still hear you. So if you have any questions, the best thing to do is to just speak up. So let's see how we did with this exercise. I would show you the wheel, but as I said, going back and forth is just not a good idea. So, but I can tell you that the person who got chosen by the wheel is Caleb. Caleb, are you with us? Where is Caleb? Caleb, are you there? Perfect. Okay, Caleb. Tell us first of all, don't give us the lead coefficient yet. Tell us first of all what you found out was the finite difference. What was that number that you got that kept, sort of being the same? And then we'll ask you what column it came from after that. But what was that number that you got that was the recurring number? Please go ahead, Caleb. 12, he says in the third. Interesting. I think I messed it up though. Okay. Well, I'm going to ask you to hold off with that answer for now, right? I'm going to see if I can get some backup for you. I'm not sure if that answer is right. Let me hear from Axa. Axa, are you there with us? Is Axa there with us? Axa, did you get the same answer as Caleb? You got 12 as well? And was it the third difference? What did you get? 12, but in the fourth. That's interesting. All right, that's interesting. And positive 12, by the way, is what you're saying. Oh, so Caleb, Caleb is now saying, yeah, he got 12, but he says it's in the fourth. Oh, okay, so let me change up things here a bit. All right. So in the fourth. All right. So Travis and a bunch of other people are jumping on board now with Caleb. So once Caleb decided to go from being the third difference to the fourth difference, they're now saying that yeah, we can sign on to that. Okay, all right. So that's your finite difference. All right, let me go to somebody else now. Thank you, Caleb. And yes, it looks like you've hit it on the right number eventually. Actually, I'm going to take you out as well, and I took out Caleb as well. So you're safe for today. For today. Uh, let's get to the actual lead coefficient now. The lead coefficient, and that job goes to Noah. So Noah, are you with us? Perfect. So we got let me move this around. I didn't mean to move that around. I wanted to move this around. Let's get to the LC now. Can you give us this whole thing is messed up now. Jeez. See if I can get it back. There we go. Can you tell us what you figured out as the lead coefficient based on all of that? So positive 1 over 2, negative 1 over 2. What was it? Positive 1 over 2. All right. What do other people think? Thank you very much, Travis, by the way. Noah, sorry. What do other people think? Right, Harry, everybody says the same thing. Excellent. So that is your lead coefficient. That's a half. It was 4 factorial this time, which is not 6, it's actually 24. So when you take the 12 and divide it by the 24, it actually works out to be a half. Absolutely. So we know the lead coefficient is a half. All right, to take us up to the 11:15 hour, we're going to come back and look at how to actually calculate the equation later on. But let's look at some questions that are in the textbook. And I'm going to be calling on a few of you in a minute. Describe the end behavior of each. These are questions from the textbook. Describe the end behavior of each of the polynomial functions. Which finite difference will be constant? Determine the value of the constant finite difference. So these are, 1, 2, 3, 4, 5, 6 questions. And let's see how we do with that. Right? Let's see if we can answer a couple of questions about them. Take Noah out. And one of you is going to tell me about that first function, the x squared plus 3x minus. We're going to answer a whole bunch of questions about that. And that goes to Kristen. Kristen, are you with us, Kristen? Kristen, where is Kristen? Oh, there you are. Perfect. Kristen, let's start off with the first question, which is to describe, let me put a little check mark beside it. Can you describe the end behavior of this function, the x squared plus 3x plus 1? You know that I have no clue. Okay. All right. Do you remember the stuff we talked about yesterday here? When we talked about, what do you mean by end behavior? When we talked about Q this to Q that, that's what end behavior is, Kristen. So we'd say, for instance, it goes from quadrant 3 to quadrant 4 or whatever, that kind of thing. So that's what we're talking about. Was in the class yesterday. Okay, you know what? I'll give you a pass on that part, but let's get to the part that we did today then. I'm assuming, Kristen, that you're going to make sure that you watch those videos from yesterday, or if you want to come and see me in that period, 3 to 3:30, that's fine. But please make sure you do that. But let's get to the other parts which we actually did today. State which finite difference. Oh, by the way, can anybody else, we'll come back to Kristen in a minute. Can anybody answer that first question? What is the end behavior of the polynomial function? I'll take that answer from anybody. We'll come back to Kristen in a minute. So you're saying 2 to 1. Ava and Rachel are saying Q to Q1. Absolutely. It's it's a quadratic function, which is an even degree function. It has a positive lead coefficient of 1. So it does go from Q2 to Q1. Absolutely. So that answers the first part of the question. Q2 to Q1. Absolutely. Okay. Let me get now to Kristen to answer the second question. Which finite difference will be constant? That's based on the stuff that we did today. Which of the finite differences is it going to be? The first, the second, the third, the fourth? Which one of them will be the constant? We're not asking for what the actual number is yet, but which one of them will be constant? Is it going to be the first difference that's going to be constant, the second difference, the third difference, the fourth difference? Which one will be constant? Back over to Kristen now. What would you say to that based on what we did today? Okay, are you looking for a hint, Kristen? Because when I call on anybody if they're stuck, I'm quite happy to give them hints. Okay, well, have you been following along with what we've been doing today, Kristen? Have you been doing the exercises that we've been doing? Perfect. Okay, so let me go back to the chart again. This chart that we did, when we took all the first differences, we said, you know what? These first differences are all different, right? They're not all the same. So this is not a linear function. Went over to the second differences column and we said, okay, these are also not the same. When we got to the third difference column, we found out that we're all the same. Do you remember that, Kristen? Okay. Do you remember that? Do you remember that part that we did? Perfect. Okay. So we've concluded that this one was a cubic function because of the fact that it was the third differences that were all the same. When we went to the second one, it turned out that the fourth differences were all 12, right? So it was this column that we got the 12s from. Hopefully you got that when you were doing it as well. So we concluded that since it was the four differences that were all the same, that must mean that it is a fourth degree function. So let's come back to this function now. What is the degree of this function we're looking at, the first function? Because that will help us to figure out which of the differences will be constant. What's the degree of that first function, the x squared plus 3x minus 1? What's the degree of that function? Yeah, I can hear you well. Yeah, go ahead. Okay. Mm-hmm. Good. Perfect. 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 So that's what the answer to that question is. Which finite difference will be constant? It will be the second finite difference that will be constant. That's the one that's going to be constant. Okay, thank you, Kristen. Okay, remember to watch those videos so you can make sure that you catch up with us. All right, so that was Kristen. And the next question I'm going to ask is, well, what is that constant finite difference? What is it going to actually be? What number is it going to be? And that question goes to Rylan. Rylan, are you with us? Rylan, where's Rylan? Perfect, Rylan. Do you know what will that number be that's going to be the same? Right? What is that finite difference actually going to be? That's what we're asking. I'll give you a break after Rylan is done. We'll do a few more of these when we come back from the break. Remember the formula that we gave you? Use that formula to tell us what that finite difference is going to be. And in fact, I'll put you on the page that has the formula in it so that you can see what the formula is. Here's the formula right here. Finite difference is equal to the LC times n factorial. Okay? That's what you're going to use to figure out what the finite difference is. It's right there. So I'll come back to the equation now. And over to you. You saw the formula I just gave you, Radin, right? Just want to make sure that you're with me here. Okay, well, let's go through step by step then. And by the way, I'm going to give you a break, but I just want to finish this up, and I'm going to give you a break after this. So, Riley, remember it says, I'm go back to I'm going to write the formula down for you. The FD is equal to the LC, lead coefficient, multiplied by n factorial. All right. What is the LC in this case? What is the lead coefficient of the function we're looking at right now, Riley? Look at the function, that's A. What's the lead coefficient? Talk about lead coefficients yesterday. And everybody else, just be patient, right? This is the way that Mr. Kamak runs the thing, right? I work with a student until the student gets it. It would be 3 you're saying. No, the lead coefficient is a number in front of the term that has the highest exponent. So it's not 3. So look at the terms of that function. All right, look for the one that has the highest exponent, and the number in front of that would be 1. Perfect. Okay. The n refers to the degree of the function. What is the degree of this function? Think back to what Kristen was saying earlier on. What's the degree of this function? 2. So it's going to be 2 factorial. Can I ask you to calculate that for us now, please, on your calculator? What does that work out to be? So the answer is 2. Perfect. All right. I see a hand going up, but I really want to give you your break. So actually, no, there's no hand going up. All right, so it's now 11:17. By my math, that takes us to 5 minutes from now, takes us up to, actually, it's come to 18. So that, I call it at 11:18. And that putting 5 minutes on it takes us to 11:23. So let's take a break for 5 minutes and come back at 11:23. Okay, we are back. All right, hopefully everybody is back with us and ready to roll. All right, Chan, are you there? Joel is here. Okay, our chat, perfect. All right. All right, so let's get back into this. And the person that just came up on my wheel is actually Joel. So, Joel, I don't know how you knew that was coming up, but you maybe had a sense or something. I don't know. But anyway, Joel, it's now your turn. So, Joel, I'm going to ask you to work with me now on, I'm just going to take another one at random. I'm just going to do C. Let's just work out C here. All right. Thank you for explaining and going over it again. No problem, Rylan. Absolutely, that's my job, and I'm quite happy to do that. And I urge you all to ask the questions when you're not sure about anything. All right, so let's get to Joel now. Was it Joel? Just double check that. Yeah, it was Joel. Okay, so Joel, here's my question. Let's start off with the end behavior of this function. What would you describe as the end behavior of C? I'm just underlining C. What would you say is the end behavior of C? Well done. Quadrant 3 to 4 is right. If there's anybody who's not sure why that answer is what it is, then you got to stop me and let me go over it some more. But if not, we're just going to move on. Thank you very much. All right, whose hand is that going up? No, that's looked like Riddy. Yes, Riddy, please go ahead. Okay, is it an odd degree function or an even degree function? Let's start with that. Good. Positive lead coefficient or negative lead coefficient? Good. No. Positive or negative? Okay, so when you combine a negative LC with an even degree, then it's going to look a lot like a quadratic function that opens down like that. Because remember, a quadratic function is an even degree function, is it not? Isn't quadratic even? Right? And if it has a negative lead coefficient like a negative a, it opens down, correct? Okay, so that goes from 3 to 4, and that's why this goes from 3 to 4. Okay? All right, great. Thanks for the question. Always want to get those questions, so please keep them coming. All right, so that takes care of that. Let's keep going now. Thank you very much for the end behavior, by the way. Let's ask the next, that was Joel. Let's ask the next question now, which is, which finite difference will be constant? And that question goes to Rachel. Rachel, are you there? Can we go over? Okay, you're here. Okay, Brooke is asking us to go over what we just did. All right, so Brooke, Was what I just explained a few minutes ago okay for you, or do we still need to do that some more? Is that enough for you? I just saw your message. My explanation was okay for you? Okay, perfect. All right. So we're back now with Rachel. So Rachel, can you tell us which finite difference is going to be constant in this case? The fourth one? Absolutely. Thank you very much, Rachel. And now comes the really, the challenging. I'm taking Rachel out for now. And that is to actually find what that finite difference is. What is that finite difference? And that question, well, okay, Brooklyn, I think was it Brooklyn earlier on? No, Brooklyn, I think it's the first for you. I don't know why I thought I called on you before and you weren't there or something like that, but it looks, anyway, so Brooklyn, you're the one that is, okay, so Brooklyn, can you tell us what that finite difference is? Can you work that out for us, please? Tell us what that finite difference is. What is the equation again? Sure. FD is equal to the LC times n factorial. Nobody else, by the way, put any answers in the chat. I'm just asking for Brooklyn right now. Okay, so he has their hand up. That's Kayla. Kayla, you're not offering an answer, right? You just have a question, correct? Sure, go for it. Of course. Yeah. All right, so Brooklyn, you saw me put the equation there for you, so over to you. Okay, so finish the question then. Okay, actually work it out. -3. Whoa, whoa, where's the -3 coming from? Why do you say -3? Back up a second. Okay, what is the lead coefficient in this equation? Not sure? Okay, let me define lead coefficient for you. No, the lead coefficient is the number that's in front of the term with the highest exponent. Okay, which of these terms has the highest exponent? There are, okay, so it is in fact -7. Perfect. It's not necessarily the first number, it's just a number in front of the highest coefficient term. Sorry, highest exponent, sorry. Could you put it all in the equation and work it out for us now, please, Brooklyn? So you're right, it is -7. That is your lead coefficient. -168 is correct. So the third answer for this is -168. All right, I'll do one more from this, and we'll do another question which is coming up shortly. Then we'll still call in a few more people. Thank you very much, Brooklyn. Right, and in every single case, right, if a person needs help, quite happy to help them out, but we're going to work with that person until they get it. The next person is Sharissa. Sharissa will do the last one, the very last one. So Sharissa, are you there with us? Where is Sharissa? Perfect, Sharissa. Sharissa, can you start by answering? Let me erase all of this here. Can you start by answering the first question? What is the end behavior of this function? What would you describe as the end behavior of this function? The last one, I want to just underline. Right, it's not Q this to Q that. That's what I'm asking for. Q2 to Q1, you're saying. I actually think about it some more. Think about it some more, because I'm not agreeing with that answer yet. Okay. If you need help, you just let me know. Okay. What kind of function would this be the closest to, a straight line or a quadratic? Which one do you think this would be? Okay, would this quadratic open up or down? I agree, by the way. Would this quadratic open up or down? Okay, so let's do that then. What's the end behavior of that function? Thank you very much. See, whenever you get to do end behavior, what I want you to do, Sharissa, is ask yourself, is it most like a straight line or is it most like a quadratic? And once you've answered that question, you can figure out end behavior. Make sense? Okay, great. All right. Thank you, Sharissa. And that's what I do, folks. If it's your turn, it's your turn. We're not going to let you off the hook, but we'll give you all the help you need until you're okay. All right. And we're all the rest of us are just going to be patient until that process is done. Let's continue. Thank you, Sharissa. You're now off the hook for today. Let's go to, looks like it's Emily. Emily, it's your turn. Emily, are you there? By the way, when I let you off the hook, that doesn't mean you must, sort of go off and start playing Xbox. That doesn't mean that you're out of the class for the rest of the day. Don't use that as an invitation to slack off. Okay, back to you now, Emily. Emily, can you tell us which of the finite differences are going to be constant this time for this particular function? The sixth difference. Well done. The sixth difference. The sixth finite difference is going to be constant. Oh, that's ugly. That is ugly. The sixth FD. Thank you, Emily. And hopefully everybody's clear on why it's the sixth one. And I'll take Emily out for now. And I'm going to be asking now for probably the hardest part of this, which is what is the lead? Sorry, what is the, no, what's the value of the constant finite differences? That goes to Elizabeth. Elizabeth, are you there with us? Excuse me. Wow, not only is she there, she's got an answer ready to go. But is she right? That's the question. Do we all agree with Elizabeth on that one? All right, is Elizabeth on the right? Yeah, right. Okay, good. So that answer is minus 720 is correct. Yeah, good stuff. All right, we're going to move on to another kind of question, similar to this, same concept, but let's just see how this one works. State the degree of the polynomial that corresponds to each finite difference. Determine the value of the lead coefficient for each polynomial function. So the second difference was equal to minus 8. The fourth difference was minus 48, and so on and so forth. So I want you to put your thinking caps on now, because I'm not telling you how to do it, but I'm telling you that you have enough information to figure out what to do. I'm taking Elizabeth out for now. And the next person on the wheel is Aliza. Oh, Aliza was absent. Or did Aliza come in? I can't remember if Aliza did show up eventually. Let's see. Aliza is here or not? Or was Aliza the person who was absent? Aliza was absent. Okay. So let's find somebody else. All right, so start thinking about how you're going to answer that question, the value of the lead coefficient for each polynomial. Keonte, your time. I have to leave for a minute. Okay, it's for a minute. Okay, Kayla. All right, let's go to Keonte now. Keonte, all right, where are you at? Where are you? Are you there, Keonte? Where is Keonte? Where is Keonte? Oh, there you are. All right, you're not sure how to do this? All right, let's do this, Keonte. Let's write down that formula again. The FD is equal to the LC times n factorial. Okay? They're saying the second differences are the ones that are constant. And they're telling you that what that FD is minus 8. So what part of this function do we know? Do we know the FD? Do we know the LC? Or do we know the N? Which of those parts? I'm going to walk you through this now, Keonte, so don't worry. We're going to walk you through this. What part of this function, what part of this equation do we know? Do we know the SR? Let's start with the first part. Do we know the FD? Do we know what the finite difference is? Yeah, FD is finite difference. What is it? What's the finite difference in this case? In the first one, for A? Minus 8. Okay, good. Do we know the LC? The lead coefficient, that is. Do we know the LC? Or is it that we're trying to find the LC? Well, look at the information that we're given, and look at the question that was asked. Right? Read the question for yourself. Right? See what the question is asking for, and see if we know the LC or we're trying to find the LC. You can read the question for yourself. Okay? LC stands for lead coefficient, by the way. Okay, so do we know the LC then or not? Not yet. So let's just put LC for now. Do we know the N? N stands for the degree of the function. Do we know what the N is? Do we know what the N is? N stands for the degree of the function. What do you say to that question, Kayante? Do we know the N is my question for you. I'm not sure about that either. Okay. Well, let's go back and look at those tables for a minute, Kayante, right? Because I'm determined that you're going to give us this answer. When we were looking at this column, remember you worked out all of this, right, Kayante? You did all of this stuff with us, right? Yes? Good, perfect. So when it was a fourth difference that was the same, that finite difference, right? That meant that the n was 4. When it was a third difference that was finite, that means that the n was 3, and so on and so forth. So what the degree of the function is tells us which difference is going to be finite, correct? Yes, Keontae, are you with me on that? Does that make sense? Okay, let's go back to this question now. Do we know the n in this case? It says the second difference is we're equal to -8. So do we know what the n is in that case? What do you think the n is in the case of the first one, of A? The n corresponds to the degree of the function. So what do you think? If you need another little hint, we can certainly talk about that, but I'm still asking you for the n, degree of the function. Yeah, what is the degree of the function? We found out that the second differences were all -8. That's what the FD was. That's what the finite difference was. So what's the n in this case for A? What's the value of the n in the case of A? That's what I'm asking for, Keontae. 8? No. No, that was what the second differences were. But there's a clue there as to what the degree of the function is, which is a different question, right? Remember, whichever column you were in, whichever differences worked out to be finite, that was the degree of. So if it was in the second column or the third column or the fourth column, that would also tell you what the degree is. So the degree is 2. Thank you very much. So it's 2 factorial. Could you now calculate what that LC is for us, please? Finish up that equation. Tell us what that LC is. You know how to use your factorial key on your calculator. Go ahead and work out what the LC is, please. What's LC equal to in this case? So I'm asking you to solve for LC. Folks, we're going to get there. So you just have to be patient. I just want to remind you of that. We will get there. We're going to give everybody a chance to get there. -16? No, sir. You write that out. Just do a little algebra for me. It's not -16, right? Do some algebra. You know that you have something times 2 is equal to -8. What is that thing? Write it down carefully on a piece of paper and work it out. Right? We're gonna get you to the answer, Keontae, but you need to write it down. Something times the LC, sorry, 2 times the LC is equal to -8. What is the LC? Write it out. Maybe call the LC x. So 2 times x equals -8. What is x? So write it out that way and tell us what your answer is. Yeah, but it's equal to minus 8, right, Keontae? The 2 factorial is just 2. We're going to call it LCX. Set it equal to minus 8 and solve it. Go. Tell us what the X is, which is the same thing as the LC, by the way. Everybody is going to learn in this class. We're all at some point going to learn this. So, as I said, and I keep urging you, you're going to have to be patient. We're going to give everybody a chance to get there. So have you written out the equation yet, Keontae? And if you have, tell us what the equation is and then solve it. What equation have you come up with so far? First part of the equation is 2x, but what is 2x equal to, Keontae? What are we saying that the 2x is equal to? Okay, solve it. What is x? You're solving an equation for x, right, Keontae? Thank you very much, sir. Does that make sense to everybody? Is everybody on the same page with me at this point? Just want to make sure. All right, does that what we just did? Perfect. Okay. All right. So I am going to take Keontae out and we're going to move on to the next question. So we've answered that one. It works out to be -4. But what about the next one? That's what we're going to go to next. All right. Everybody follows what we're doing so far, hopefully. All right. So I'm going to erase all of this and I'm going to go down to, let's go to 60. Let's do the last one and then we'll stop this. So let me erase this here. And now we're doing F. This is the last one. All right. So Keontae out. And who else is left now? We got Neil. Neil, are you there? Where is Neil? Perfect. Okay, what is this? Is that 60 or 50? It's 60. Fifth difference is equal to 60 is what it says. Okay. All right, so Neil, thank you very much. Your time. Can you help me out and walk us through what your answer is? Or just give us the answer, because we want to move on. So just give us the answer. What would you, if you need help with it, then let me know. I can write the formula down for you again that the FD is equal to the LC multiplied by n factorial. So what would you say is the answer this time? Neil. FD is equal to 60. Yeah, that's right. And n is 5. That's also correct. Yes. Well, the n is 5 in the n factorial. Yes. Okay. So go ahead and work out what the, yeah. Go ahead and work out the LC for us now, please. Okay, so what you have there is, let's see, two, not so sure about that. Not so sure about that. I'd like you to try it. Hold on, did I get that right? Yeah, I'd like you to try that again. By the way, Keontae, I apologize. I said sorry. That wasn't meant. I didn't mean that in any way to, but that was a mistake on my part. Sorry about that. All right, back to Neil. I'm not agreeing with two. Sorry. Let's try again. Let's go through the steps. Let's do this, Neil. Let's try to set this out. What is the FD in this case? What do I put for FD in this case? Let's go through this as one step at a time. Can't find the button for n factorial. Okay, so fine. Why don't you just take you agree that it was 5 was the factorial. Take the 5 times the 4 times the 3 times the 2 times the 1. Do that. Just go through that process. If you can't find the button for that, that's fine. Right? I know it's a longer way to do it, but let's just do that part. Well, what is the FD first of all? What is our FD in this case? Let's put it into the formula first. Use the calc on Google. Oh, okay. All right. Fair enough. Yeah, so back to you, Neil. What's the FD? Let's put it into the formula first. What's the finite difference that goes into the formula? Right? I need to put something for FD. What do I put for FD? So Neil says 60 is equal to the LC times 5 factorial. Perfect. So can you help me out now? And I see that, let's say, I think it was somebody, Keontae was suggesting that you could use, there's some calculator on Google or something like that. So let's see if that can work out what the LC is first. Sorry, the 5 factorial is. What is that 5 factorial? What did you get for that? Back to Neil, by the way. Is 120? Okay. So what's the LC then? That's still my question. What's the value of the LC? Solve that equation for us, please. Similar to what we did with Keontae a few minutes ago. All right, solve for the LC, 0.5. Thank you very much. Okay, so we're going to finish up this stuff that we're doing now by asking the question, well, could we actually get the equation of the table of values? Is it okay if we put a half? Of course, yes, absolutely, Noah, absolutely. Is it okay? Is it okay? Can we actually get the equation of the function? Right? I'm going to take you back now. Actually, I'm going the wrong way here. I'm going to take you to this same table that we had at the beginning. And can we all agree on this? That, first of all, this is a cubic function. I think we agreed on that already. This function is cubic. Does anybody remember why we know that, by the way? How do we know this is a cubic function? Can anybody remind me why we know this function is cubic? Anybody? I'm not spinning the wheel on this. I'm just asking. Anybody? Okay, so Janaya's raised her hand. Okay, and I see some people put something in the chat there. Third differences are the same. Okay, Janaya, can we agree with what everybody's putting in the chat there that the third difference was the finite difference, so therefore it must be a cubic function? Can we all agree on that? Yeah. Mhm. Well, yeah, but I put this here before I asked the question. I probably should have put this, should have hidden that away, right? Before we knew that, I'm saying before I wrote that down, how did I know it was cubic? And the answer to that question is what people have been saying. It was the third column, the third differences that were the first finite differences that were the same. Okay, so here's a general format for a cubic function. There is a cubic term, there is a term to the power of 2, there is a term to the power of 1, and there's a constant on the end, right? So can we actually figure out the whole equation? That's the thing I want to ask. Well, we knew one part of this already. If you remember, we'd work this out. Let me take you back to that page for a second here. We'd worked out that the LC was minus 2, right? Hopefully everybody remembers that. So I actually know the A already. That part I know. I can put that in. So it's actually y equals minus 2 x cubed. We still don't know the b yet, so let's say bx squared. We still don't know the c, so let's say cx. And we apparently don't know the d either. So it's not much information to go on. And I'm saying that we can still work out what the equation is. And anybody suggest how this table of values might help us to get either the b, the c, or the d. Can the table of values help us with that? Look at the table of values. Is there anything in the table of values that you think might give us that information? Look at that, folks. How did we get the 2? The 2. You mean it was minus 2 already, not 2. It was minus 2. The 2x, where did I put 2? It was minus 2x cubed. You mean that 2 there already? Is that what you're asking about? There's no other. Oh, because remember when we were doing this a while back, I'll take you back to the second page. We worked out that the LC was minus 2. Remember that? The lead coefficient of this function is minus 2. Remember we did that? Is that okay? So I'm just using that information right now. And I'm saying that I can write at least part of the equation, the lead coefficient. Lead coefficient is what's in front of the x cubed, as minus 2. That part I know. I don't know the b, the c, or the d though. And I'm asking, is there anything in the table that can help us to figure out the b, the c, or the d? Can anybody, what do you mean the y-intercept is 1? How do you know that, Noah? What makes you think the y-intercept is 1? Yeah. Ah, you got that? Everybody caught that? Noah just said that I know what the x-intercept, sorry, the y-intercept is. Y-intercept is actually 1 because that's when x is 0. So that's absolutely correct. So we can rewrite this now as y equals minus 2 x cubed plus bx squared plus cx plus 1. Why? Look at the table. When x was 0, y was equal to 1. That means that the y-intercept is 1. The y-intercept is always that constant on the end. The constant on the end was d, so we'll make that equal to 1. All right, is everybody with me with that so far? Does that all make sense so far? All right, let me check in with the room on that. Right? How about you on that, Rylan? Rylan, how about you on that? Does that make sense, Rylan? Where's Rylan? Rylan. Rylan going once. Where's Rylan? Where is Rylan? All good? Yeah, okay, that's good, Jeremiah. Where's Rylan, though? Looking for Rylan. Earth to Rylan. Where's Rylan? All right. So, I take notes of all of this, folks. It's not good if you're supposed to be in the class and you're clearly not there. All right. So, I'm going to come back to Rylan, but for the time being, looks like everybody else seems to be okay. So the question is, all right, so we've got the A and we've got the D. How are we going to get the rest, the B and the C? Can anybody suggest something that we could do that might give us the rest of this equation? Any ideas? Any thoughts on that? The B and the C. Any suggestions as to how we can get the rest of this equation? Anybody? Nobody? Well, we have a table of values. Can that help us out at all? Right? Because I think we can get the equation of this line. Right? We have the lead coefficient, the minus 2. We have the constant of the n. So there's only two things we don't know. We don't know the b, we don't know the c. There must be a way we can use that information in the table. Nobody has a thought on that? What if I do, okay, Jeremiah, go for it. We got that, yeah? Mm-hmm. Mm-hmm. I'm going to give you a little thumbs up on that, right? 2 thumbs up on that. Well done. So, and Karis, by the way, well done. So what I'm going to do is I'm going to pick 2 points on the table. Let me pick 1 and 7. I don't like to pick numbers that are going to give me too much work. So I'm going to pick 1 and 7. So what I'm going to do is I'm going to plug in 1 and 7 into this equation. When x is 1, y is 7. Okay? So I'm going to put 7 is equal to minus 2 times 1 cubed plus b times 1 squared plus c times 1 plus 1. So really all I've done is I've said, okay, I know that 1 and 7 are matched in the table. 1 gives me 7. So why don't I put that into the equation? So let's complete this. So 7 equals, well, 1 cubed is still 1, times minus 2 is going to give us minus 2. This is going to give us 1 squared times b, which is just plus b. This is plus c, plus 1 is equal to 7. Well, you know what? I have 2 variables, though. So that's not enough for me to solve this. By the way, why don't I take everything else, put it on the other side? So let me put this, let's put the minus 2 on the other side as a plus 2. So 7 plus 2 minus 1 is equal to b plus c. So I took the 1 and made it to a minus 1, took the minus 2 and made it to a plus 2. So that means that b plus c is equal to 8. So hopefully we can all agree on that. Right? Is everybody on the same page with me on that? Does that make sense? B plus C is equal to 8. Yes, thank you very much. Thank you. But that's not enough information because you cannot solve for 2 variables with 1 equation. You need 2 equations. So what Karis and Jeremiah were saying earlier on is pick another point. Now, for me, I like to make my life easy. So I'm going to pick a point like minus 1 instead. Now, minus 1 leads to 15. So let's do the same thing all over again. Minus 1 leads to 15. So 15 is equal to minus 2 times minus 1 cubed plus b times minus 1 squared plus c times minus 1 plus 1. How did you get the original minus 2 at the start of the equation? Travis is asking. Thank you for the question, Travis. So when we were doing, I'll take you back to that again. When we were doing the first differences, second differences table, we actually worked out that minus 2 right there. The LC was equal to minus 2. You remember that, Travis? That's what you're talking about, right? We worked that out. So that's where the minus 2 is coming from. We do know what the lead coefficient is. The lead coefficient, number in front of the number in front of the x cubed is minus 2. So let's go back to where we are right now. Whoa, sorry, that's too far. So let's keep going. So 15 minus 1 cubed is minus 1. Minus 1 times minus 2 is 2. This is going to be plus b. This is going to be minus c plus 1. And you should check the math on that for yourself. I make mistakes sometimes, but I don't think I made one here. Minus 1 to the power 3 is minus 1. Minus 1 times minus 2 is positive 2. Minus 1 squared is 1 times b, which is b. And then minus 1 times c is minus c. Okay, we'll do the same thing here. We're going to bring the 2 and the 1 on the other side. So 15 minus 2 minus 1 is equal to b minus c. So this is going to be 12 is equal to b minus c. Okay, so no, so there would be no c. How do you isolate? Okay, let me go back again. Let me go see what the questions are because I missed a couple of questions here. Couldn't you just isolate the b to c and then plug it in? Yeah, but we need 2 equations though, Noah. Right? We still need 2 equations. Yeah, and we now have the second equation. So what I'm going to do, right, is I'm going to use elimination because I find that easiest. So we have 2 equations. I'm going to circle 2 equations that we have. We have 1 equation here. We have a second equation here. I'm going to combine those using elimination. So I'm going to say that b minus c is equal to 12. and b plus c is equal to 8. And what I'm going to do is I'm going to add these equations together. I can add them because adding them makes the c's get eliminated. So I'm going to get that 2b is equal to 20. You all need to remember how you did this back in grade 11. Grade 10 when you had linear systems. And of course, there are different ways to do it. You could use elimination, you could use substitution. Doesn't matter to me which one you use. But at any rate, I'm adding these and the c's are going to drop out. So that means that b is equal to 10. Once I have the 10 for b, I can now figure out the c. So 10 plus c, I'm using this one now for substitution. 10 plus c is equal to 8. And therefore c is equal to 8 minus 10, which is equal to minus 2. So I now have the whole equation. I'm ready to go. Yes, Shania, please go ahead. Okay. So if you're asking me are you asking me where the 1 and the 7 came from, for instance? Is that part of your question? Mm-hmm. Okay. Yeah. So we picked combinations of x's and y's from the table. One of the combinations, let me just erase this here. One of the combinations was the 1 and the 7. So when x is 1, y is 7. So what we did then, Janaya, is we said, okay, why don't we plug in a 1 and a 7? Every time we have an x, we plug in a 1. Every time we have a y, we plug in a 7. And that's where the first equation came from. Of course, I had to simplify it down, and I ended up with the first equation. And then we said, okay, let's get another point. So we chose the other point to be 1 and minus 1 and 15. So I did the same thing again. I plugged in a minus 1 every time I had an x, and I set it equal to 15 for my y. Does that help you out, Jeremiah? Does that kind of show you where, Janiah, sorry, where it all came from? Okay, because you cannot, we still have two variables, and you cannot solve for two variables if you don't have two equations. It's just not possible, right? So we need two equations, and then once we have two equations, we can use a linear system, like what you learned in grade 10 with elimination and substitution and that kind of thing, for you to solve the second one, okay? To solve the two variables, okay? Okay, good. So here's what we have. We have the A, the B, the C, and the D. We can write it all down now. Let me just put a little thing on the side here. My A was always minus 2. My B, we said, was 10. My C worked out to be minus 2. And my D, we said, was 1. Remember, we got the D, by the way, by just looking at the table of values. 0 gives us 1. Oh, sorry. 0 gives us 1 right there. So that's why my D is 1. So I'm ready to write my equation now. Here comes my equation. My equation says that y is equal to minus 2x cubed plus 10x squared minus 2x plus 1. No. You say there would be no c. Could you just say that? Okay, right. So the question is this equation right? Well, what I would do if I was doing this, if I had a test and I had a question like this, is I would go back and just check one of these other points in there. I'd plug in maybe the 5 and the minus 9 or the 6 and the minus 83 and make sure my equation does work, right? So why don't I go ahead and since we're doing that, why don't I plug in maybe let me see, let's go to 4 and see if 4 gives us 25. We'll try that. Because if at least one other point works, then we're probably right. So I say y is equal to minus 2 times 4 cubed plus 10 times 4 squared minus 2 times 4 plus 1. What we're hoping for when we do this is that the 4 is going to give us 25? Because that's what the table of values says. So let's see. So that's equal to minus 2, 4 to the power of 3, I happen to know should be 64, plus 4 squared is 16, times 2 is 1, times 10 is 160, minus 8, plus 1. I'm doing a lot of this in my head here, folks, so I might need you to bail me out in case I make a mistake. Minus 128 plus 160 minus 8 plus 1. All right, you know what? Time for my calculator. I don't know if I can do this all in my head. Minus 128 plus 160 minus 8 plus 1. I'm getting 25. So at least, looks like we're good. All right. Do these pages get posted? Not just the pages, Axa. I told you I'm actually recording the entire video. Okay? I'm going to stop recording this one now because we're going to go on to the next thing. I'm going to at least start the next one. I don't know if we're going to be able to finish the next one, but I'm going to stop. Actually, you know what? I won't stop recording because I can easily edit it afterwards. So I know some parts of this were a little bit much, but are you mostly with me on this? And yes, you can go back and watch the video later on and sort of slow it down and stop it and pause it and rewind it as much as you need to. But did most of that kind of click with the class? What do you say, folks? Give me a little thumbs up or something there. Okay, good. That's a good reaction. All right. Take a 30-second breather while I set up for the next part of what we're going to try to get through today.